So we have here a new example. We have a triangular load, okay, that is acting in our beam. So we draw the shear and moment diagram and compute the shear and moment equation. So we have this beam, okay. The first thing we do here is to compute for the reactions at 1, or let's say that's R1 and R2. And take note that our unit here is in terms of English unit. So we can summation of, let's say, if we want to compute R2 first, so we have summation of moment at 1 is equal to 0. That's counterclockwise positive. So therefore, we have positive R2 times the moment arm, that is 9. Correct? Then minus, now our triangular load here has a resultant force, and the resultant force is just equal to the area of our triangular load. So therefore, our resultant force is 1 half times 270 times the length, that is 6. And our resultant force is acting, that is 2/3 from this point. Let's say that's 2/3 of the base. And from point B, that is 1/3. Okay, that's the centroid of our triangle. So we could have, that is the triangular load, that is 1 half times 270 times 6, okay, times the moment arm from A, that is we have 2/3 of our base, that is our base is 6, that is the length of action of our triangular load, and is equal to 0. So we have our R2 here, 360, and our unit here is in terms of pounds, okay, since we have this one is in pound, then we have feet, so the first one will also feet, so we can cancel out feet here, so the remaining would be in pounds. Okay, then we can now compute for the R1, so we can just summation of force vertical 0, upward is positive, then we have R1 plus R2, they are positive since they are acting upward, minus the resultant of the triangular load, that's 1 half times 270 times 6, okay, that is equals to 0. So we have the value of R1 here, and since we know that R2 is 360, so we have the value of our R1 here, that is equal to 450 pounds. Okay, so we have already determined the reactions, in which R1 is 450 and R2 is 360 pounds. And now we can now proceed to the determination of the shear and moment equation. But first, let's decide on where we are going to cut our beam. Now in this case, we know that our beam or segment A to B is continuous. Okay, we do not have other distributed load here other than 270 pound per foot, so therefore we can say that A to B is continuous. And B to C here, we do not have a load, so therefore it has a different shear and moment equation as the shear and moment equation for segment A to B. So we can cut this into two. Let's say this is our section 1 and this one is our section 2. Okay, so if we cut our section 1, and we know that our section 1 is X distance from our A, so let our A there as our reference point. So we measure our distance of our cut section always from A. So therefore our section 2 here is also X distance from A. If we cut at section 1, we could expose our internal shear and as well the internal moment, and we assume them as positive. So if we try to isolate this section, okay, so this would be our cut section 1, in which at section 1 we have our internal shear 1 and internal moment 1. And then we could also include our reaction at A, that is 450 pound, and the portion of our triangular load. However, if we cut at that point, take note that our height of our uniform load here is unknown, okay, since our height here is varying as we are changing our distance. So as our distance is changing, also our height or the magnitude of our triangular load is also changing as well. Okay, so therefore we have varying value of y. So in that case, we could create a relationship of y with respect to x by ratio and proportion. So we could say that our y here, by ratio and proportion, that is equal to, we have the height over the length, that's x, is equal to the height over the length of the largest triangle. If we have our height is 270 pounds per foot, then we have our length is 6 feet. So we could say that our height here is 270 over the length that is 6. Okay, so we could have our y, this similar triangle. Okay, so if you try to do similar triangle, we have this one. This is y, x, 270 is to 6. Okay, this is the 6. So therefore, our equation is 270 over 6 x. That is the value of our y. So we could come up with shear equation, that is we have to sum up forces vertical is equal to 0, upwards are positive. So we have here RA, or let's say that's 450 pounds. That's upward, so that means it's positive. Then minus the internal shear 1. Now we have the resultant of our triangular load here, let's say that's R. Okay, now take note, our R there is equal to the area of our triangular load, that is 1/2 y times x. This is the area of a triangle, correct? Now we know that our y is 270 over 6 x. Okay, now take note, we still have 1/2. So 1/2 times 270 over 6x times the x, okay, since this is y. So therefore, we have our resultant there, that is equals to 270 over 12 x squared. Or we can simplify it as 45 over 2 x squared. So this is the resultant in terms of x. So therefore, this is 45 over 2 x squared. So we have our resultant that is downward, so minus 45 over 2 x squared. Okay? And it's equal to 0. So we have our shear 450 minus 45 over 2 x squared. So this is our shear equation 1. Now let's create a moment equation. We just need to sum up moment at section 1. It's equal to 0, counterclockwise positive. Then we have negative 450 times the moment arm from section 1, we have x, minus or plus the resultant that is rotating counterclockwise, so therefore that's plus positive, the resultant of the triangular load, that is 45 over 2 x squared, times we have the moment arm. We know that the resultant force is in 1/3 of x, now distance from our section 1. Okay, that's 1/3. So therefore we have 1/3 x plus moment 1 is equal to 0. So we have our moment equation here, that is equal to 450x. Then if we multiply 45 over 2 and 1/3, you could get 15 over 2. Okay, minus 15 over 2 x squared times x, that's x cubed. So this is our moment equation 1. Okay, so we have now computed the shear equation and the moment equation. Now let's try to cut our section, okay, our beam into section 2. So if we cut our section at this section 2 here, we have our reaction included in our section, and we also have the entire 270 pound-foot triangular load included also in the cross section. Okay, we have now this cut section 2. Again, our x here is from 6 to 9 feet. Again, since our section 2 here is from B to C, and that is 6 feet to 9 feet with our x here from A. So we can now compute or determine shear equation by summing up forces vertical is equal to 0, upwards are positive. Then we have the reaction 450, this one here, and then minus the resultant of the triangular load, and this resultant here, that is the area of the triangular load, that is 1/2 times 270 times the length 6. Okay, this resultant. This is the resultant. And then we have the shear, the internal shear is acting downward. We have minus V is equal to 0. And then we have shear here that is equal to negative 360, that is in pound. Okay, so we do not have variable x here since we do not have a load. So therefore, our shear diagram is in 0 degree order. Okay. Now for moment, we sum up moment is equal to 0, counterclockwise are positive. Then we have negative 450, the resultant, times the moment arm x. Okay. Then we have plus the rotation of the resultant of the triangular load, but the resultant is 1/2 times 270 times 6. And the moment arm, the distance of our resultant to our section 1, we have here, since we know that this is 1/3, okay, this one is 1/3 of 6. If we have 1/3 of 6, we have 2. So therefore, this is 2 meters, correct? That is the location of our point from this point. Let's say that's B, correct? From B, that is 2 meter. Now, since we are referring our moment arm from this, then we should have this distance. Okay? Now, this distance, since we know this is x, and from the resultant to A, we have 4 meters here. Since we have 4 plus 2, we have 6. Okay? So, therefore, this location of our resultant from section 1 is x minus 4. So, x minus 4. So, we have here the moment arm x minus 4. The resultant times the moment arm. And then we have the moment that is counterclockwise. So, we have plus m is equal to 0. So, we have here the moment equation that is equal to 450x minus 810x minus 4. This is the moment equation of section 2, and this one is the shear equation of section 2. Now, let's try to draw our shear and moment diagram using these shear and moment equations. Okay, so I have here the tabulation of all the shear and moment equations that we have computed. So again, this moment equations and shear equations is valid only for 0 to 6, that is from A to B. Okay, and this equation here is valid only from 6 to 9. Okay, that is from B to C. So now let's compute the shear first at leftmost point of our beam, or that is at point A. So since we are dealing at A to B, so we need to use this equation. So we have shear equation 1, so at x is equal to, then we have 0 since we are at point A. So we have our shear equation is equal to 450. So we substitute x equal to 0 at this point here. Okay, at this equation. So we set x equal to 0. So our shear is 450. Okay, that is in pounds. Since 45 over 2 times 0, then we could get 0. So the remaining would be 450. So therefore, at A, we have 450. That since that is positive, then we plot it here. Let's say that is 450. Now, let's plot our shear at point B. So we have x is equal to 6 feet. Okay, that's at point B. We have, then since we are still dealing with segment A to B, then we are still be using this equation. And that is, we have our shear at B. That is, we substitute 6 as a value of x in this equation. Then our answer would be this. We have 450 minus 45 over 2 times x is 6 squared is equal to negative 360 pound. Okay, so therefore, since we have negative, so we go below our shear diagram. So we have here So we have negative 360. Since our load here is in first degree, so therefore our shear diagram should be in the second degree order, that is curvature. But take note, as what you can see, if we have this kind of load, okay, that is increasing, okay, in magnitude, so we have our load shear diagram that is frowning. Okay, so if our load here is increasing in magnitude and it is acting downward, okay, so it is acting downward, but at the same time it is increasing in the magnitude. So we have our moment diagram that is second degree and it is frowning. Okay, so that one. Now what if we have load like this one? Now take note, we have different consideration again if we are referring to load diagram. If we have a triangular or first degree order in our shear diagram, the only basis in drawing or in determining the curvature of our moment diagram is just by knowing if it is increasing or decreasing. If it is increasing, therefore our moment diagram is smiling. Okay, if it is decreasing, our moment diagram is frowning. But in this case, that our load is triangular, so we cannot use those mnemonics or rule of thumb in plotting or drawing our shear diagram. Okay, now if we have this kind of load again, take note, it is negative since it is acting downward, but take note it is increasing in negative, so therefore we have a frowning shear diagram. But in this case, it is acting downward, so therefore negative. However, it is decreasing in negative, so that means we have smiling diagram, smiling shear diagram. So we have different rule of thumb for load diagram in relation to our shear diagram. And then, since we know that we do not have load from B to C, okay, so therefore, if we use the equation for shear at B to C, we can we realize that we do not have variable x at this point. So therefore, we have negative 360 internal shear all throughout from B to C. Okay, so therefore at this point we have negative 360. So this is now our shear diagram. Okay, how about for moment diagram? We have, I'm using this equation here, that is we have at x equals to 0, so let's start at point A. We have our moment equation that is 450, then we set x here is equal to 0 minus 15 over 2 times set x equal to 0 raised to the 3, then we have 0 moment. Since again we have a ruler or hinge at this point, so therefore we should not have moment unless if this is fixed, okay, fixed support, then we have a moment at that point. So therefore we have 0 moment at this point here. However, we have a point here in our shear diagram in which our shear is equal to 0, okay, at this point. So we need to compute our moment at this axis here. Okay, however, we do not know yet what is the location of our shear when it is equal to 0. So we need to determine first what is the value of x. So by using the shear equation of segment AB, so we are using this one, okay, 450 minus 45 over 2x squared, wherein our shear at that point is equal to 0. So we are going to look for the value of x. Okay, kung asa dapit ang location ni 0, ni shear 0, so we have our equation that is V is equal to 450 minus 45 over 2 times x squared, okay, and we know that our shear should be equal to 0, so we get the value of x is equal to square root of 20. So therefore, the location of our shear when it is 0 is square root of 20. So we have square root of 20. Okay? So using this value of x here, we can now compute the moment at this point. Using the moment equation 1, this of our section AB. So this one, 450x minus 15 over 2 x cubed. So we have at x is equal to square root of 20. So what is the value of our moment when our shear is equal to 0? Okay, so we are computing here for our moment. So we have m is equal to, the equation is 450 times x, is that is square root of 20 minus 15 over 2 times square root of 20, then it is raised to the 3. So we have our moment here that is equal to 1341.64. And the unit is in pound foot. So therefore, we have here 1341.64. So at this point, okay, now what is the curvature of our moment diagram? So since again, our shear diagram is decreasing, as what you can see here, so therefore we have frowning moment diagram. Now take note that our shear diagram here is in second degree. Okay, so this one is in second degree. Since our load diagram is in the first degree, so therefore if our shear diagram is in second degree, our moment diagram should be on the third degree curve. Okay, this is a third degree curve. So this is not parabolic, or this is not quadratic anymore, or this is an equation that is in the third degree. Okay, so now let's compute the moment at point B. Okay, we have this equation that is the same equation, 450x, okay, at x is equal to 6 feet, okay, or that is at point B, 6 feet from A. We have the moment that is equal to 450 times our distance, and this distance from A, that is 6 minus 15 over 2 times 6 cube, and this gives us 1080 pound feet. Okay, so we have here at this point, let's say that is 1080. So we have again our moment diagram is decreasing, so therefore we have a frowning moment diagram curvature. So we have this way. Let's proceed to segment BC using this equation of moment. Okay, we have 450x minus 810x minus 4. Then let's compute the moment at B when our x is equal to 6. So our x is equal to 6. So what is our, or at point B, what is our moment using the second equation? That is 450 times x, this one. Our x there is 6 minus 810 times 6 minus 4. So we have our moment here, and it should be equal with 1080, and that it is equal 1080 pound. Now let's compute the moment at C using the same equation. We have at x is equal to, now our x here is 9 from A, 9. So what is our moment at point C? That is the same equation. Moment is equal to 450 times 9 minus 810 times 9 minus 4, and this should be equal to 0. So therefore our moment at this point is 0. Okay, however, how are we going to plot this one? Our shear diagram is in 0 degree, it is horizontal, therefore our moment diagram should be in the first degree. So therefore we have a inclined line that has a constant slope. So we have, okay, this one. So therefore we have already done, or we have completed the shear diagram and the moment diagram. And in this case, our maximum moment is 1341.64, and this will be used in designing the cross section of our beam or this structure here. Okay guys, so if you have question, please comment it down. For more videos, please don't forget to like and subscribe. So thank you very much for listening.